Hi guys, this is some kind of improvised video about Tiny Tracer. Tiny Tracer is a tool made by Hashresade, and it serves for tracing Windows APIs and NT APIs and basically function calls with parameters. It's also able to trace I think Linux syscalls and Linux library functions, but I will focus on the Windows. So I tweet this basically about new feature of Tiny Tracer. So basically tracing syscalls. And what I mean with syscall, because syscall is the call to some service routine, and basically when you program some application, you are just for example, calling create file A or create file W, and it just goes to syscall into ntdll, like ntcreate file, and after that it goes to ntos kernel and other things. So to kernel, uh, uh, Tiny Tracer enables you to basically trace the syscall assembly instruction, which serves for directly calling a syscall routine, like ntcreate file to ntos kernel. So basically, whenever some kind of syscall stop code is used, you can trace it with user mode tracers. So this is a very good feature, and I basically show some showcase here, and after that I scrolled it down and found that, hey, this is awesome, you should do a tutorial in your case. And I think, yeah, because I try to annotate the pictures as much as possible, but I think that little short video and little improvised video about this could be quite useful, and also a little bit some kind of uh, thank to the Hashresade for the awesome tool, because the features are extremely awesome. It's basically insane. For me, from my point of view, it's one of the API monitoring tool, one of the best one nowadays. Yeah, we probably know everybody about the API monitor, but it's quite outdated, and the support for Windows 10 it's not so cool. And this one works well, and the developer is excellent. You can check the pull request and issues on the GitHub and or wiki, and yeah, it's insane. So good job, Hashresade. Good job. So okay, I will start with the compiling of the pin, because it's covered nicely in the wiki of the GitHub page, but I want to show you it's very fast, and there is no issue. So we will compile the Tiny Tracer, and Tiny Tracer is based on pin tools from Intel. So it's a dynamic binary instrumentation tool, and after we compile that, we need to do a little bit modification, because to the settings of the Tiny Tracer, because we will be tracing APT29, some kind of routine. I think it's quite interesting to show, and it's covered in this showcase. So let's start. You can see the link to the Tiny Tracer here. So let's check it. Okay, and here it is. So you can check your releases, and we can download the latest release source code, and you can see here that it requires Intel pin, and I'm sorry, but Intel does not allow distribution of compound pin tools. Okay, no problem at all. If you don't know how you can basically build it, hey, it's here. There is one of the best wiki page I found so far. You can see how to build on Windows, and click here, and there is very good guide how you can do it. Hey, it's basically no issue at all, and very good. So these things will be covered in this video. I want to repeat myself again. So let's start. First of all, also check the README, and in the README you can see that it was tested with Intel pin 319 and 322. So we will download 322. Okay, here, and Intel pin. So we downloaded Tiny Tracer, and we need to download Intel pin. And if you remember, it was tested with a 322. So just use the tested version from the Hasherazade. There, you don't want for her to troubleshoot something she didn't test it. Yep. So for 322, and here. Okay, it's downloading. And after that, we will basically compile it, build it. There is very good guide about how you can do it, and I will show you basically. We will do the, you can see on the wiki page, the installation, and on Windows you can see that the pin should be like unpacked to root directory. So if you don't want to modify some installation path and other things, so we will unpack it to root directory. Okay, so here it is, and here is the pin tool, extract files. Okay, and we can delete this one. Come on. Yep. We can delete this one, and Tiny Tracer, unpack it. Oh, yes. And delete this one. First of all, we just change it to Tiny Tracer. And here it is. And this one, we need just this one, directory extract or cut, paste. Come on. And we need to modify the name to pin. Let's grab the Tiny Tracer and paste it to source, tools, and here. So it's here. Nice. And we have it prepared. So now it's time to grab that, the pin tool with the Tiny Tracer, and copy that to the root directory. And here it is. So now go to source and tools and Tiny Tracer, and here is the project, this one. And we need to retarget the SDK. She's mentioning that in the wiki page and other things. Okay. And yep, retarget complete. And switch to the release mode. And we need to build a 32-bit version of the Tiny Tracer DLL and a 64-bit version of Tiny Tracer DLL. So let's build it. Build Tiny Tracer 32-bit in release mode. And no issue, no warning. Hey, I love that. Come on. Yep, build succeed. And now switch to 64-bit and build again. Now basically two DLLs were created. I will show you. So close that. Don't save it. And here we are. And we are in the Tiny Tracer, and you can see that in the release is oh sorry, Tiny Tracer, and where it is tiny tracer. Yeah, in release, here is the 32-bit, and here is the 64-bit tiny tracer DLL. And we need to move it basically to install folder. And here is some kind of a batch file. Like, yep, it's here. Sorry, it's here. Move DLLs bat. Yeah, basically this one just moved the tiny tracer 32-bit and 64-bit to the install directory. So let's run it. Oh, sorry. Yep, and you can see it here. It's moved. So now if you check the install directory, you can see here that the tiny tracer 32-bit and 64-bit DLL are located here. Nice. And we are prepared. That's all. That's all. Yeah, so we have it here prepared and built for the tracing. So we just grab that, and I will copy that into my VM. Come on, come on. Yeah, sorry, VirtualBox. And let's wait a little bit. So after this, we will also add the registry entries to spawn the tiny tracer in the context menu. So let's grab that, go to C and copy that to the root directory. And it's here. Just go to source, tools, and tiny tracer, install 32, and add menu. Add menu basically adds it to the context explorer context menu. So basically, if you right click on the exe file or DLL, you can basically trace it. In the context menu, it will be shown. Add menu, yes, okay. So for now, that's it. I don't have it some kind of exe file here, but basically with the adding to the registry, we just do some things like wait, I will show you. Exe, we will try to find some exe file, and with the adding to the with the add menu registry, we basically did create a context menu for the tiny tracer, like say here. You can see here, run with pin tracer, tiny tracer, and run as administrator. Okay, so this is done. So we have successfully compiled it, we have built it, and it's prepared. But we will need to do some modification to trace our APT29 sample. So from here, it's all. And let's grab the sample. So go to my GitHub page. So APT29, I released some good, or hopefully good analysis about APT29 and APT29 GitHub, and Dumb Guy is my GitHub page. Dumb guy. Hey, I don't know. I know it sounds good. You know, I firstly wanted to have dumb guy, real dumb guy, dumb with the B, but it was already yeah, somebody already has it, so I choose this one, and it's quite interesting. As you know, I'm so dumb that I basically choose P instead of B. Here you can see the malware analysis report APT29. Nothing interesting, but yeah, here is quite a long analysis about it. I think that maybe some guys like it. So here you can basically download the sample and add a database. You know, the add a database quite get me some time. It takes some time. It took some time to create this. So if you just download it and check it, I will be very glad. So download it, and we will use this thing, the sample from this. So let's go to downloads, and here it is. We will switch to full screen, sorry for that. Okay, And now we will unzip it, extract files. Okay, and password is infected as VX underground, the same way. Yep, this is it, and here we are. So, okay, another one. So we need to extract it to 7-zip, extract, okay, infected again. And here we are. And here we can mount it, but I don't want to mount it. I want to extract it with 7-zip again. I really love the 7-zip. It's insane tool. And here it is. We can copy that here. Test. And here it is. Basically, it's very okay, it's interesting, but it's quite simple. You can here see link file. The link file is executing NVEXE, which is basically normal and signed binary from the Acrobat, and this one basically sideload VC runtime, which has the spoofed import entry for acrosub64. And this one, the acrosub, this one module we want to trace because this one is the main malicious module. All malicious code is inside this module. So we have prepared this, and we have here also the IDA database. So let's check the database. And I want to show you what we want to actually trace. And you can replicate, you can do all steps by your own, what I'm doing here, because all these things are available on my GitHub page, Tiny Tracer, free open source from Hasherazade. Hey, that's cool. So you can see here that we are in DLL main, and here in the DLL main, what you can see here, immediately some kind of free console and other things, and here is something what is quite interesting. You can see this database took me some time. It's already annotated and retyped, extremely retyped. I mean, like every instruction, every function, everything is retyped. So you can see here is the anti-create rate X, but what it is in real case is basically here is some kind of, you can see it here, I already applied enums in IDA, so this basically resolve syscall. So it's the resolve syscall is doing some kind of hashing of syscalls and resolve the syscall via the hash, and basically the return value goes to EAX. You can see it here, and EAX is basically where the syscall number is located before the syscall assembly instruction is called. And yeah, this is basically the stop code. Stop code, something what you can normally find in anti-DLL. Yeah, for the routine of anti-create thread X. You know, there is a ZW create thread X. It's basically mean from the user mode, it basically mean the same. If you call ZW create thread X from the user mode, from your normal application, it will just jump back to anti-create thread X. But if you call ZW create thread X from the kernel mode, it will call the ZW create thread X routine. What are differences between the ZW create thread X and anti-create thread X in the kernel is basically less check are performed in the ZW create thread X from the kernel mode, because you know it's basically routine for kernel, so it already thinks like, hey, the kernel developer already know what he's doing. So anti-create thread X just has some more checks. And you can see here the assembly, the syscall instruction. Yeah. So basically, I retyped the function, and it looks like this. Very nice. So I want to trace this function, DLL main. Yeah, man, I want to trace the syscall, I want to trace the get module handle, I want to trace, and what I want to trace, I want to show you get thread context, set thread context, and resume thread. Why? because here what you can see is basically thread execution hijacking. And we will basically hijack the start routine of the new spawn thread. You can see here basically that decoy routine RTL new security object with multiple inheritance. I don't know what does it mean. Yeah, but we can get the address of this function, and this address is set as the started routine for the new create thread newly created thread. You can see that the thread is created in the suspended mode. And if you create a thread in suspended mode, it's not already initialized. It's not initialized yet. So what does it mean? You can't change when you get the thread context of this thread, newly created thread. You can't change the RIP register, RIP, which basically points to the next instruction, next instruction pointer. So because it's not initialized yet, so you need to change RCX. Why? You can see it here. It's a thread execution hijacking, and hijacking via context RCX register. New thread is in suspended state, not yet fully initialized or initiated. RCX is the first parameter for RTL user thread start. So whenever the thread is created, it will be basically in suspended mode. It will be checked. It will be waiting in RTL user thread start, and first parameter is in RCX register for this routine, and it points to thread entry point. And thread entry point is basically a real start routine of the thread. So if we modify it, we can do the same. If we, for example, if this would be, there will be no new created thread, and we will basically just get context of the current thread and set context, we can modify the RIP, because the thread is already initiated. But in this case, no way, because the thread is not initiated, and we can't modify RIP. We need to modify RCX, which is the first parameter for RTL user thread start, and which points to thread entry point. Nice. So what I wanted to cover, tracing these things, tracing the syscalls, the syscall assembly instruction, and also tracing the get thread context and set thread context, and compare the context content before and after the modification. We can confirm that RCX was modified via the tiny tracer. It's extremely, I think it's awesome. So okay, this one we want to trace. So as I already told you, we need to do some modification in the tiny tracer. So first of all, just go to run me bat file. Open it, and what we need to do is we need to change the module which will be traced, the main module, because defaultly the main module which is traced is your exe file. Your exe file, or the one you actually run. So for example, in this case, it will be the nvexe. So if you trace it, it will be trace this one. But we want to trace this one, DLL. So we want to trace, we want to start this one, but trace this one, DLL. No problem at all. Just copy the name. Go here, and here you can see somewhere is settings for it. Target up, target module. Where is the target module? I can't see that. Yeah, here, target module. You can see it here. By default, it is the main module, so the exe file you are running. But it can be also dealt within the trace process. Hey, it's very, very good help. So what we need to do is this one. And that's all. First one, checked. So we will be tracing this library in the main process. So save it, and okay. What is next? The next is that we want to enable, because we want to trace also the syscalls. And I want to also, if I want to grab the like the thread context, the context is a structure, and this structure is quite large. It has like hundreds of bytes. So I want to basically get this argument bytes. So we need at least 256 bytes, like for the main registry and other things. We don't need all structure bytes, but we need the basic one for the main registry. So let's just go to tiny tracer ini, which is basically a very simple config file, and here is the hexdump size. So whenever it will try to trace the thread context, it's able to basically, here is the pointer to context, which is the structure, and it's able to basically write you what is the pointer address and what is the content, yeah, on the address. So yeah, it's good. So here we want to basically dump at least 256 bytes. And here is somewhere here trace syscalls. So trace syscalls will be true. Yep, trace syscalls true. We want to trace that, and we want to also modify this one. Save that. And okay, so correct. And the last thing what we need to do is here the parameters. This one file is basically telling you what functions what functions will be traced in the way that we will get the parameters values. So we need to trace the things we want to focus on in this function. So for example, this one, it's a kernel 32 routine. So copy that, and you can see that the type is that it basically grabs it takes 3 parameters. So take that, and you can do it like this. Here, kernel 32 DLL, but without the DLL, and parameters count 3. And okay, what is next? We can trace the get module handle A with basically again kernel 32 DLL and 1 parameter. You can see it here. So again, a number of parameters is 1. Get proc address. I think that I have no get proc address. Yeah, get proc address is already here. So we don't need this to do it by our own. But here is get thread context, set thread context, and resume thread. So first of all, get thread context. This one. Another one is set thread context. This one. And resume thread. And this one. So we should trace all of this. And here again, kernel 32. If you don't know from which library it's called, like that it's in a kernel 32, hey, just copy the name, go to imports in IDA and find it, and here you can see kernel 32 DLL. Okay, set thread context. Oh, sorry. Here and here. This one takes 2 arguments. This one takes 2 arguments, and this one takes 1 argument. Nice. But now we will be tracing this function, but now we want to trace the syscalls. Hey, here is the wiki page, how you can basically add some entry for tracing the syscalls parameters. So we want to do that. So what we can actually do, like tiny tracer GitHub Google Things. Hey, again, wiki page from Hasherazade, extremely awesome. Wiki, and here you can see something, how to trace syscalls, yeah, with ND parameters. Nice, you can see it here, and this one is example. Nice, so we have it here, and we need to do something like that, but we need the syscall number and number of parameters for our routine. So we need to trace, we want to trace the entity create thread X, and but what is this syscall number in our investigated operation system? Because syscall numbers, like for example, now syscall number for entity create thread X differs from version operation system version to version. Yeah, so for example, on Windows 7 it's absolutely different number to Windows 10, some kind of specified build. Yeah, so it very differs from version to version, from build to build. So we need to find out what is our syscall number for entity creator X. And I actually create quite a tricky script here. When you, again, GitHub, or we can go to the history and go to my page. Here it is, about the APT, and you can see here that I have somewhere here a Python script which basically will do the what I described here. Python script. This Python script will parse the ntdll, and it will just show you for your current system what are the syscall routines and their numbers. So we need to download the script again. Okay, no problem. And raw and download this. Save. And just go to downloads. And we will grab that and put it to some Python temp. And here it is. Ooh, we can actually, if you check that what it does, what it's doing, you can check that basically it just grabbed the ntdl, but be careful, the 64-bit version of ntdl, and our sample is 64-bit. Yeah, so no problem with that. But if you encounter you are dealing with some kind of 32-bit, you just need to change the path to the sysvol64. And yeah, I will not cover how this script is doing that. Yeah, what is the tricky things here, but it works. So we can actually run it. So PowerShell, and let's run this script and get some routine numbers, the syscall numbers, Python and resolve, yes, and we will put it to syscalls txt, and we will open it in Notepad. Syscall txt. And this works. This should work. I don't know. We can see. Nice. You can see it's a very extremely difficult and sophisticated script. So, all right. As I already told you, from the user mode, the syscall numbers like ZW create thread X and NT create thread X, hey, these numbers are the same, the syscall numbers. from the user mode is the same routine, from the kernel mode is different routine. So, but the syscall numbers are the same. So we need to find zw create thread. Okay, thread x. We need to x one. Here it is. And you can see here syscall name, syscall virtual address, syscall number. Hey, here is the syscall number. So just copy that, go to parameters, and here modify the syscall number. Because if you remember, it was in the wiki page. And if you check that, here, syscall number, parameters count. So syscall number is this one. And parameters count. Yeah, actually, anti-creator X takes 11 parameters, but TinyTracer is able to trace a maximum at 10 parameters. But we can actually we can write 11. It will be the TinyTracer will trace at maximum 10 parameters, no issue. And that's it. So we have what we needed. We modify the parameters which will be traced and the number of that. And okay, we don't need this, we don't need this, and for now we don't need this. What is here? Here is the, yep, this is the IDA directory. This is the unpacked version. Here we don't need this, and here is this one. So now we set the the module which will be traced in our process is the acrosub 64 acrosub 64 DLL. We already set it. We already said that we need to modify the number of bytes which will be printed with the TinyTracer when the pointer is pointing to some memory. So it will grab that memory and print the number of bytes. We also modified the parameters, and that's all. That's all. We have everything, or I think at least. So now the thing is basically we can run it, but yeah, we can run it. Let's run it with TinyTracer. And you can see here what are the traced functions with parameters, and it's running. Come on. It's still running. We can see that the tag file was created already. What is here? If we check it for very fastly, yeah, it's still doing something. Yep, it's done. It's done. Okay, we can check that our process is not running anymore. And yep. Here is the tag file, which was created by the TinyTracer. So for this purpose, I will be using the Sublime because it has nice feature. Hey, download the latest version. Okay, no problem. Because I want to set the syntax to something what will be better for showing the things. Come on, come on. And I prepared here one script I will need later. we can call it, for example, test Python. Yes, install, and go to this one. And okay, test. And now we are in the Sublime, and we need to go to tag file. And here we can see something, but I want to see better syntax view, so let's change it. And I found quite nice the batch file. Yep, it's quite nice. And here should be something what we were interested in. Okay, no, this one is not the one I wanted. This one. Yep, you can see it here nicely. So if you check that, 2EAB is a relative virtual address of the routine from where it was called. 2E8B. Check that in here, but we need to set here the options general and check the line prefixes in graph view, and check this one and check the address. Sorry, I will do this one. 2EAB. Yeah, the module base in like the base address in portable executable format is 1800000. Yeah, but in this case, I think the ASLR is enabled in this library. You can check it here in, for example, pver. Go to optional header, and check the DLL characteristics, and you can see here that DLL can move, which basically means ASLR is enabled. And what it means, it basically means that whenever it's loaded in some kind of random address. So the relative virtual address is the same, 2EAB, K32 get process image file name, and you can see it here. Hey, what's happened here? Here, 2EAB. And what we specified, it's traced. You can see here also the syscall number and arguments. Remember, maximum number of arguments is 10. And here you can see the get thread context and set thread context. And we remember when we said that 256 bytes of max hex dump printing is here. So what you can see, this one is actually pointer. Get thread context is a pointer to context. And this one is the context content, thread context content in raw bytes. So it could be quite nice. You can see from the start, we traced it very successfully. Yeah, hey, okay, it's very good. You can see the module handle, anti-DLL, and you can see the get proc address, the decoy routine, what we saw here, the RTL, new security, blah blah blah, and you can see here the syscall. Here you can see the syscall. And you can see the syscall number again, as we specified, C1. And here we specify the parameters, and you can see here the parameters. For example, you can see the second argument. The second argument is, I think, the desired access, thread all access, and you can see it's I already applied enums, but it's OX1FFFFF. And if you check that, OX1FFFFF. Nice. This is correct tracing. And here you can see the get thread context, set thread context, resume thread. And this one is actually a good one. because you can see we can compare this thread context to this context, and we can find out what was modified. In this case, we can try to find out RCX value, how it was modified, RCX, because the RCX should point to the new thread entry routine. So how we can do that? How we can do that? If you can check that, we can see here something. It's an hexadecimal character, hexadecimal, it is hexadecimal encoded, but if the byte is printable, it's shown as printable. I don't know how can I use this kind of format like hexadecimal, but also the printable are shown as printable in C language. I don't know. If you know how you can use that immediately in the C language, just write me down in the comment below this video. But for this purpose, I will use Python to convert it to hexadecimal and CyberChef also. So first of all, this one is before. Yeah, it's the get thread context before. So we will use the Python, and the Python is quite easy to use, like before t context. Yep, and it's bytes. These are bytes, and we can basically do a print and before hex. And as you can see, it just converts to string. Yeah, this one to this one, and we need it because we want to get rid of the printable character. We want to convert it to hexadecimal 2. Let's run it. And we want to do the same for the after one. Come on, yeah, here it is. And we want to do the same for the after one, like after context, thread context. Like this, and we need to change this to this one, context. So we will grab these raw bytes of thread context, and we will convert it back to the structure. And it's super easy when we will use the C language and some kind of programming skills. I don't have much of that, but it's still enough for this. Yep, and we have it here. And let's convert it and run it. After, before, and we will just grab these bytes and convert it to something what is usable in the C language, or I'm aware it's usable in C language, and I already created some code to convert these raw bytes to the structure of the thread context, and we have it here. So first of all, we grab this one is the before, the one before. Go to the CyberChef, go to here, and from hex to hex, and limiter is this one. Grab that, and this one is before. Now we will jump back here, and I already prepared here some kind of code in C language, and you can see basically it grabs raw bytes of the thread context, and it goes here to the byte array, and the before and after again byte array, and it will be converted to the thread context structure. So if we put a breakpoint here, we will just see in the debugger the structure already parsed. Yep. So if I need to explain that, basically byte array, and here is the pointer to byte array. The pointer could be casted to the type of p context. P context is pointer to thread context structure, and we have pointer to context structure, and we will convert it to this value, to the structure of a thread context. The pointer again to the structure value. That's all. So you can see, remember, switch to 64-bit because we are dealing with 64-bit, and I'm using the here some structures, and the structure differs for the 64-bit and 32-bit. So we are dealing with 64-bit thread context, so switch to 64-bit. And we need to replace the before one. It should be 256 bytes, as we already specified. Hey, come on. And paste it. This one is the before. This one is after. And we need to grab the after one. Here and here, just grab this one. It should be the after. According to the tiny tracer, yep. These two are just converted values from the tiny tracer. Yeah, get thread context before some modification was applied, and set thread context and resume thread. You can see the same thread ID. Go to here and paste it here. Okay, once again, I don't know if I copied the right one. And copy this one and paste it to here. You can see it should be a little bit different. Yep, if you check that, some things are very it's the same, some things are same, but some things were modified, and we will figure out what. Now we can debug this one, so we don't need this one. We don't save that, but we don't need this one. And okay, let's check that. Go to IDA and go to this here. So let's debug it and break on the breakpoint. Oh, sorry, here is 257 bytes. So I basically something probably 257, 257, 257. Okay, no problem. And here you can see we break on this, but we can see here the structures already. Yeah, the context before and context after. You can see the context before. For example, the RCX register. Here. Yeah, this one is context after. And here is context before. Sorry. Context before. And here is RCX register. So we can basically just grab the context before. This one value is enough, copy, and I will be using the 101 register for some fast modification, like this one. Yep. This one, because I want to show you the differences. So whenever I want to show some things, it will be good to have it side by side. So first one is prepared, and second one is the context before. And this one will be context after. Copy, and we will do the same thing again. And this is the one after, the thread context after. Okay, and here it is. Now we will put it side by side, and like this one. And here we have context before and context after. You can see that some things, some like DRO, I think. DRO 1, 2, 3 shouldn't be modified. Here you can see many registers, many thread context things are not modified at all, but I want to show you how was modified. Like you can see here, the main registries like RCX. The RCX in this case, you can see it here, RCX, how was modified. Yes, here basically was some value, and here is now some kind of routine. Check the relative virtual address 3540. So it means that our module, because there was already ASLR enabled, so our module was loaded on the address 7FFAOD2A0000. So we can just grab this address, go to here, go to IDA, and we can rebase it, because here is the module base according to the PE header, but here we can see that the module base was different one. It was because of the ASLR. So we can go to either go to segments and rebase program, and like this one, and okay. Okay, where am I? And again, F5, decompile view. And we need to go somewhere here. Synchronize to segregate. And what we need to know is basically this RCX value was modified. You can see before it contained some value 419 in hexadecimal, and after that here is some kind of address. So let's check the address. We know that basically this one address goes to RCX, yeah, for thread execution hijacking. So let's jump to this address, and we can see this address. Yep, copy that, go to here, let's run, for example, PowerShell here, and here 0000 7FF AO D28 3540. So we confirm that basically we recovered the thread context from the raw bytes traced by Tiny Tracer to the structure type. We confirmed that the registry, some kind of registry, were modified. We confirmed that RCX was modified to point to the routine, which will lead to thread execution hijacking and other things. I think it's actually cool that we can do these things with the Tiny Tracer. And yep, so basically this was all. Yeah, we confirmed that the thread context was set as we expected. We did it with the Tiny Tracer, so this is insane. Yeah, but that we can actually get the byte content. We can specify how much memory will be grabbed from the pointer pointing to some memory allocation, and yep, I really love that. And this one is self-explanatory. I hope you enjoyed it. I hope you enjoyed it. I hope I covered the scenario here that we basically traced the APT29, the main module function, and I covered as many things as possible, and I hope you enjoyed it. Thank you for watching. I hope you learned something about the Tiny Tracer, the extremely full of feature tool and very easy to use. So thank you for watching and see you next time.